Hello students, in today's class we will read a very important concept in the current electricity chapter, and that is electrical energy and power. Now the first question which arises is, why is this concept is an important concept? It's because electrical energy will define the amount of the electrons' motion as well as how much power these electrons while on motion can have. Then we connect the wires together, we make a circuit, and we aim at transferring the electricity from one point to another point. In that duration, the whole electrical energy is not traveling from point A to point B. Okay, but some amount of the energy is dissipated, some amount of the electrical power is useless or is wasted. So what is that amount? Why is it happening? What is electrical energy? So how these household circuital systems are working? What are the things, the areas which needs improvement, and how beautifully all these things are understood under the concept of electrical energy and power and applied in our day-to-day life will be understood. So this is a very practical topic. Once you have understood, it will give the basic construction image of circuit in your mind, and hence we can proceed to the upcoming sections where we will read about the resistors, about the cells, about Kirchhoff's rule, and various other electrical instruments. Learning all these things will need the basics. One of the most important basic was Ohm's law and resistance provided by the conductor, by the insulator, or by the semiconductor. Every element or every material provides resistance, only the amount or the magnitude of resistance differ in these cases. Okay, now the another one is the electrical energy and power. So if we see only our energy concept, all the materials have their own electrical energy. Every material do not have the same amount of energy. Electrical energy is higher in the conductors, lower in the insulators. So if I'm saying it's higher in the conductors and lower in the insulator, it is very much important for us to know what exactly is electrical energy. So electrical energy is a energy which is by the virtue of the motion of the electrons in a given material. Okay, the kinetic energy of the electrons which is converted into the electrical energy. And we can say when these electrons show zigzag motion, in that case the energy generated, motion, due to motion only one sort of energy is generated, that is kinetic energy. It's the expansion of kinetic energy, because this kinetic energy of motion of electron is used in the conduction of electricity. This kinetic energy of electrons, which is by the virtue of motion of electrons in the material, constitute electrical energy. Now for power I will say that power will be more in case resistance is provided is less, and if the resistance provided is more, the power of the conduction will be less. Just think how powerful you can be. If you are fighting with a child, comparing to the child, you will be more powerful. If you are fighting with a wrestler or a bodybuilder, you will feel that the resistance provided by the wrestler or the bodybuilder is very high and your power is lesser comparing to the wrestler or bodybuilder. So exactly in the same way, here the concept of power works. More the resistance you will provide, our electrical circuit will feel its power is less. Okay, so that is one of the concept you should understand practically, so that we can know why we are using the copper wires in our circuit with a given ratio of its diameter. Have you ever seen the thick copper wires? No, we have seen very thin and many copper wires in a wire. Just cut a wire, like normally don't cut any wire which is in use. A wire which is broken, you can get that and cut it. Okay, if you will cut this wire, you will find there are many thin copper wires in it. Why so many thin copper wires? Why not a thick copper wire? Instead of many thin wires, one can have a single thick wire. Why not? Because we have already read that R equals to rho L upon area. Okay. So when we come to the resistance is inversely proportional to the area. Okay. So in such a case, what will happen is, if you will go with a thicker wire, it will not be suitable for a good powerful conduction of the electrons. Its resistivity will keep on, like, will fluctuate according to the area and the length of the wire. Okay, so we will move to electrical energy. First we will read the relation of electrical energy, and then we will read the relation of power with respect to the current provided, the voltage it is having, the resistance provided to the system. Like, there are three main concepts in the electricity: V, I and R. That is voltage, current and resistance. So according to that we will see. Okay, let's move to the point number 1. Consider a conductor with endpoints A and B in which current I is flowing from A to B. We have considered a conductor. This is one of the conductor, and this point is A, this point is B, and some current I is flowing through it. This is flowing in the direction of A to B. Electrical potential at A and B are denoted by V of A and V of B respectively. So the potential, electric potential over A is VA and over B is VB. Since the current is flowing from A to B, A have higher potential than the B, and the potential difference across AB is given by this equation: V equals to V of A minus V of B. Because current is flowing, here more charges are there. Hence they are flowing from A to B because we have lesser charges over B, from higher potential to lower potential. That is a normal flow. Whenever you will see a normal flow, let's say the normal water flow, the normal temperature flow, the normal fluid flow, or the normal potential flow, it will always be from higher concentration to the lower concentration. Okay, always remember, whenever we are not providing you any condition, take that the flow is from higher concentration to the lower concentration. So we will understand from this concept that potential at A is higher than the potential at B. So between them is a potential difference, and that is given by potential of A minus potential of B. As potential of A is greater than the potential of B, their operation will give us a positive value, and a positive value is always greater than 0. We'll take one example, like at A we have 10 volt of potential and at B we have 2 volt of potential. Now what's going to be the potential difference between A and B? It will be 10 minus 2 volts, which is equals to 8 volt. Is it a positive or a negative number? It's a positive number, and a positive number is always greater than 0. So this is what this particular formula wants to convey. Now moving to the next point. in time interval del t, it is a very small time interval, an amount of charge that is moving from the point A to B is del q equals to I del t, travels from A to B. Okay, this is the amount of charge that is moving from the point A to the point B in a time given by del t. In the very first class, we have read that our current is given as charge per unit time, that is q upon t. From this particular equation, we are getting I equals to q upon t and q equals to I into t. But t over here is taken as infinitesimal small, and the charge transferred is also infinitesimally small. So it comes to be del q equals to I del t. Now, the potential energy of the charge at A by definition was QVA, and similarly at B it is QBB. Okay, I'll explain. See, what they are saying is potential energy is given by charge into the potential at that particular point. We have read this concept in chapter number 1. Okay, potential energy equals to charge into potential at that particular point. Okay, so over here it will be q v of A will be the potential energy, that is u, and over here it will be u equals to q v of B. That will be the potential difference at point B. Okay, thus change in the potential energy del U of potential is given by final potential energy minus initial potential energy. Initial is at A. This is initial point. From here all the charges are starting, and this is the final point. Here all the charges are coming and getting dumped. Okay, so our change in potential energy is final potential energy minus the initial potential energy. So that can be written as del U equals to QV of B minus QV of A. Now, if I remove the Q out, we are taking the small q, so it should be del Q. Removed out because it is the common, so it will give us V of B minus V of A. See over here, the first equation, it gives us the potential difference. It gives us the potential difference. But here we have VA minus VB. So whatever the solution in this particular equation will come, will get reversed in the magnitude. Reversed in the magnitude, that is, the sign will change. So this will give us del Q into minus V, and we will get minus V into del Q. From this equation, we know that del Q is I into del T, that is current into the time taken. So this equation will become V into I into del T. So this is a negative result. The magnitude over here is negative. Magnitude is negative. Hence, this is smaller than 0. Change in potential energy is smaller than 0 or negative in this case. Change in potential energy is negative. Okay. Now, if charges moved without collision through the conductor, their kinetic energy would also change so that the total energy is unchanged. Like we have seen in this particular conductor, these electrons are going through a random motion showing many collisions. Okay, but we have taken the another case where the motion is systematic, and they are hence showing no collision during motion. So when they are showing no collision during the motion, the total energy of the system is unchanged. Their individual energies are changing. Change in individual energy is there, but total energy remains unchanged. In that case, there we will see the conservation of the total energy, and from the conservation of total energy, it implies that change in kinetic energy is equals to minus of change in the potential energy. Change in kinetic energy will be equals to change in the potential energy, but their magnitude will be reversed. Their direction is reversed. So, if we are applying over here, in the previous page we have seen del of U potential is equals to minus of V into I into T. Okay. So, what will be the formula for kinetic energy from here? It will be kinetic energy equals to minus of del U, and it will give minus of Vi del T. Minus and minus will cancel each other and we will get V del T into I. This will be our answer. See over here, I V del T, which is positive in magnitude. Positive in magnitude. When this is positive in magnitude, it is greater than 0. It is greater than 0. Moving on. Thus, in case charges were moving freely through the conductor under the action of electric field, their kinetic energy would increase as they move. Because, see, these are the electrons. We have applied the electric field. Now they will show a systematic motion from one end to the another end, and when they are moving from one end to the another end, they are started increasing in their energy also, because there is no interruption. While movement, no interruption, and as there is no interruption, what is happening? Their velocity is increasing. Electron increasing. When this velocity of electrons is increasing, what exactly is happening? That kinetic energy, which is equals to half mv square, is also increasing. Now this kinetic energy is increasing and increasing. So throughout this conductor, if electric field is applied, the electrons will show the systematic motion, and hence the kinetic energy will keep on increasing as they are going to move. Okay. Charge carriers do not move with acceleration but with a steady drift velocity. This is because of the collision with ions and atoms during the transit. Whatever is carrying this charge will move with the drift velocity. They are getting drifted towards the forward direction, but they will not get accelerated. Okay, their motion will not show any acceleration. The increment in the velocity will not be seen, because dv upon dt is what known as acceleration, change in velocity. with respect to the time gives us acceleration. So we are not seeing any dv upon dt. That is not seen, not seen. We are saying what is drift velocity is there. The electrons or the charge carriers, I will say, charge carriers are being drifted from one end to the another end. Okay, from one end to the another end, these charge carriers are being drifted, and this happens because these charge carriers are colliding with the ions, with the atom during the whole transit. Now during collision, the energy gained by the charges thus is shared with the atoms. The atom vibrate more vigorously, that is, conductor heats up. This is again a very star marked point. You should keep an eye on this. You have to understand why we do not go for the bulky systems. More the short, more the thin the system is, less the concept of the system getting heating up is there. Like if we are using a conductor which is having a bigger size, will take little time to heat up because there are more atoms to be provided with the energy, and then when the atoms got the energy, then they will start vibrating, then they will start getting heat. So it is a slow up process. Once the conductor, a bulky conductor, gets the heat, it's very cumbersome process to reduce the heat of the bulky conductor. That's why a short conductor or a thin conductor is used in our electrical circuit. Why so? A thin conductor, though gets heated up easily and earlier, it also reduces or it also loses its temperature easily. Okay, we are not supposed to see that always the temperature is increasing in a bigger time, but we have to see that how much time it is taking to cool down. Have you ever seen the fridge? Like, of course you all have seen the fridge. Everyone have fridge in their household. So if you go and check the sides of the fridge, they will be higher in temperature than the inside. Inside we have condenser and the cooling system which provides the cooling. So whatever heat is inside the refrigerator is taken by the conductors or the metallic bodies present in the refrigerator to the outside. There is a sink outside the refrigerator where they dump all the heat. But what happens over there is, if we see, there is a heat or some heat, some amount of heat which the conductor aim at spreading at this surface of the metal. So why do they do this? Why they are spreading to the sides of the refrigerator? Because once they have like spread the heat to the all the surfaces, more the surface area, more will be the reduction in the temperature. Area and temperature are inversely proportional. If you will give more area, there will be more cooling down. You can see this concept even in the winters. In winters, we sleep by getting closed totally. Even we try to rub our hands and we try to make ourselves shrink in us. Like mostly we lay like this. This is the position of laying, okay? But in case of winters, how do we lay? We lay like this. Okay, we will be more closer. Sometime even more closer than this. We will be like this also. Okay, almost closing everything and coming nearer to our own self so that there will be less surface area and we will be accumulating little more heat in our body. So same happens in the cases of conductor. What exactly they do is they spread the heat throughout so that the reduction in the heat is more uniform and more faster. So this is one of the best example of refrigerator, and another one is a refrigerator is the bulky metal body. If you switch off the refrigerator, it takes minimum 1 hour to reduce its temperature. In normal fridge of something like 200 plus capacity, liters of capacity, it will simply take 1 hour for the fridge or the sides of the fridge to cool down after we switch it off. So why this happens? Because the metal from inside to outside is having heat, and slowly it reduces its energy, vibration reduces, and then it cools down. So bulky the metal, more time it takes to cool it down. We'll come back to the point. During collision, the energy gained by charges thus is shared with the atoms. The atoms vibrate more vigorously, that is, conductor heats up. So this is our conductor. In this we have electron, we have provided the electric field, and they are vibrating. Now when they are vibrating, this energy is given to the atoms from electrons to atoms. Okay. And then from these atoms, what happens? These atoms start vibrating, and once they start vibrating, they start accumulating the energy in them, and this energy accumulation heats up our conductor very much. Now heating of the conductor, how it affects the ability of the conductor, we're gonna read. Thus in an actual conductor, an amount of energy dissipated as heat in the conductor during the time interval del t is given by del omega I V del T. So this is the amount of electrical energy that is either wasted, or we can say is dissipated as the form of heat. Amount of electrical energy, we can say it in two ways. It's like it got wasted, or dissipated in the form of heat. Now the energy dissipated per unit time is the power dissipated. Energy dissipated per unit time equals to power. Okay, so del W is the energy we have seen in the previous slide, which is dissipated upon the time del T. So what was the value of del W? It was VI del T. Now over here time is del T divided by del T. It will give us VI, which is equals to power. Now understood how come the formula of the power came. We didn't do anything. We were just proceeding with the electrical energy. Now this electrical energy dissipated per unit time gave us the power. Now we will use the Ohm's law. This is the formula of the power, which should be remembered very well. This is very important. We'll see, using the Ohm's law, V equals to IR. We have seen voltage is proportional to current in the circuit. We have removed the proportionality sign, so it gives us Ri, where R is proportionality constant or the resistance. Okay, so P equals to IV. First thing from here, now V equals to IR, right? We will substitute at the point of V. It will give us P equals to I into IR. So it will become I square R. Other thing is I equals to V upon R. I equals to V upon R. Now in this case here, in place of I, we will substitute it. We will get P equals to IV. P equals to V upon R into V. So P equals to V square upon R. Okay. So this is one formula. This is another formula. I'll write over here for a proper understanding and reference. V equals to IR, P equals to IV, hence P equals to I square R, P equals to V square upon R. So these are the formulas over here. As the power loss is ohmic loss in a conductor of resistance R carrying the current IE, the power loss is known as ohmic loss. Power loss equals to ohmic loss. But in cases of conductors, not everywhere, but in the cases of conductors. Now it is this power which heats up, for example, the coil of electrical bulb to incandescence, radiating out the heat and light. You have seen the olden bulbs where we have this tungsten filament in the bulb which heats up and the light will come. This heats up due to this heat only. This heat which is generated as a product of electrical energy. So this is one of the best example of using these electrical energy in any system. Now we need an external source to keep a steady current through the conductor. Why do we need? We just want to keep something steady current, okay, through the conductor for knowing how this power basically works. So we have made one circuit in which, as we can see, there is a steady current flow through the conductor. In this simple circuit shown with a cell, it is the chemical energy of the cell which supplies this power for as long as it can. So see over here this diagram, I will explain it with a red ink. This whole thing is electrolyte. Electrolytes are a solution in which you will find positive and negative ions. This is a negative electrode and this is a positive electrode. Current is flowing from the positive to the negative, and here all these electrons are attracted to the negative. All these electrons from this negative are getting repelled. Electrons repelling. And these electrons are being attracted by this positive electrode, and they are moving from this positive electrode like this to the negative electrode like this, and hence the circuit is completed. Electrolyte is completing this circuit because it have ions which show the motion. We have another good thing over here, which is the resistor. If there is no resistor, just for a minute, if we assume that there is no resistor existing, then what exactly will happen is that the whole system will keep on flowing the current continuously. There will be very less heat dissipation through these wires. Lesser heat dissipation through wires in case we don't have resistor, okay? But because we are having resistor, this resistor will provide resistance to the motion of electrons, and hence when this resistance is provided to the motion of electrons, this will be like providing more dissipation of heat. This will slow down. So at a point will come, this time in round 1, initially if we say 10 electrons are moving, then it will reduce to 9, 8, 7, 6, 5, 4, and a time will come when it will be 0. That is, after that there is no power supply, no motion of electrons, and no electrical current, okay? So this time will also come because we have given a resistor. In case like there is no resistor, in that way also there will be a point when there will be no flow of current, but it will take a long time duration. But because we have provided a resistor, in a shorter time we will see that voltage is dropping. See what the figure states. Heat is produced in the resistor R, which is connected across the terminals of the cell. The energy dissipated in the resistor R comes from the chemical energy of electrolyte. At a point, the electrolyte will not have any chemical energy to supply. This is what our second statement is saying. I'll read the statement once again. In the simple circuit shown with a cell, it is the chemical energy of the cell which supplies this power for as long as it can. Equation 6 and 7, this equation and this equation. I'll write over here P equals to IV or I square R or V square upon R. Shows dependence of power dissipated in resistor R on the current through it and voltage across it. Power dissipated is actually proportional to I square and V square, because from Ohm's law, see why I have written this voltage is proportional to current, because I want to make sure that you all remember R is not a factor, but it is a proportionality constant. If R is removed, then power is directly proportional to I square and V square. More the current and more the voltage, more is the power. By if power is increased by 1, current should be increased by a factor of square. Okay, if you need 4 watt of power, 4 watt of power, in that case I should be 16, current should be 16 amperes. In that case voltage should be 16 volt. So power and current and voltage are related by a factor of square. Now this equation 7 has an important application in the power transmission. What was the equation 7? Equation 7 was I square R and P equals to V square upon R. Electrical power transmitted from power stations to homes and factories, which may be hundreds of miles away, via transmission cable. These are the transmission cable and electricity is supplied from here to here. They are very far away. So in this case, one obviously wants to minimize the power loss in transmission cables connecting the power stations to homes and factories. If there is more power loss, they will not be able to travel the long distances. Power loss more, then transmission is less. Okay, consider a device R, which is a power P is to be delivered via transmission cables having resistance RC to be dissipated by it finally. The V voltage across the R and I, the current through it then will be P equals to VI. What we have given is, this is our device R, okay, and this R have a resistance value of RC. Now the voltage across this device is V and current in this device is I. So the power will be given by VI. The connecting wires from the power station to the device has finite resistance. R, C is not infinite. Okay, it has some numeral value. It is finite. It comes as 1, 2, 3, 10, 100, 1000, something like that. The power dissipated in the connecting wires, which is wasted, is PC. PC is the power wasted. PC equals to power wasted in the system. So PC equals to I square R, and this will be equals to, from this I we will substitute the value of I here. I is from this equation I equals to P upon V. Here it is I square, so this will become P square RC upon V square. Thus to derive a device of power P, the power wasted in connecting the wires is inversely proportional to V square. Power is proportional to V square, but power wasted is proportional to 1 upon V square. ठीक है, PC and P are related by a factor of RC upon V square. RC upon V square. Resistance by the square of the voltage. So we have seen this one thing, that power equals to, no, first of all we'll start with the very small of derivation so that we understand what we did in the previous hour in this section, so that I can explain power dissipation more nicely. Voltage is proportional to the current in a given circuit. Then voltage equals to Ri, that is resistance into our current. Now we have our power equals to IR, I square R, power equals to voltage into I, and power equals to V square upon R. Okay, now if we say that R is proportionality constant, so in this way we will remove this proportionality constant from here and we will make it proportional. P is proportional to I square, P is proportional to V square. What is this? This is the power transmitted. Power transmitted from initial point to final point. Okay, now we have taken a device which is having resistance RC. We have provided voltage of V across it and current I. Now power which is transmitted is given by VI. Okay, now another thing, power which is dissipated or useless, dissipated equals to I square R. Okay, RC is the resistance. So this, from this equation 1, from equation 1 I have P transmitted equals to VI and I equals to P transmitted upon voltage. So power dissipated equals to I square RC. We'll substitute the value of I over here and we will get power dissipated equals to power transmitted square upon voltage square into RC. So what we have got from here is, this is power transmitted, but see over here we will get power dissipated is inversely proportional to the voltage square, whereas this is directly proportional. So this is the difference I aim at telling you, sharing with you. Hope you understood the last point in the previous slide. Now let's get summarized what we have read today. We have read the electrical energy. Okay. So electrical energy can due to either kinetic energy or potential energy. Mostly it is due to potential energy, which is energy stored due to the relative position of charged particle or electric fields. Its symbol is E and its units are joules or electron volt. Formula is given as E equals to QV, where Q is the charge and V is the potential difference. Examples where electrical energy plays an important role are static electricity, batteries, lightning, electrical charges moving through a wire or electricity. Electric charges moving through wire or electricity, lightning, batteries, static electricity, electric wheels generate electrical energy, audio speakers, doorbells, and so on. Now uses: lighting, cooling, heating, operating appliances, electronic computer machinery, public transport system. Computers, public transport system, and etc. Now the facts which we should be aware of, like it's kind of a fun factor. So few facts if we will know, we will better remember what is electrical energy. Electricity travels at a speed of light that is more than 1,86,000 miles per second. A spark of static electricity can measure up to 3000 volt. A spark of electricity can measure up to 3000 volt. Just see, a spark can measure up to 3000 volt is a very big voltage. That is why it is ultimate to die for a person who gets an electric shock. Now a bolt of lightning can measure up to 3000 volts, okay, or we can say 30 lakhs of volt. Lightning can measure 30 lakhs of voltage, which is again is a very high voltage. Even like 10,000 voltage are there in our electrical generators. Touching that particular point is extremely avoided, or they have shown a board over there, the restricted place. Just think, a lightning with 30 lakhs of volt, how much damage it can create. It can actually ruin a proper our village or a town or a whole building. It can smash down. So lightning are that dangerous. And this particular lightning volt is, we can provide this particular as a rate, that is 30 lakhs volt per second. It is not within a second the lightning will come, will give you 30 lakhs of volt, and it will ruin everything within a single second. So that is how it is so dangerous. But still, the use of the sciences, the use of the physics and the rules of the physics is making the use of electrical energy in a very useful manner, and we are using this electric current in our day-to-day life, and we are enjoying it. So if we study the science behind a concept, behind a principle, behind a natural occurring things, we can use even the dangerous as in a best possible way. That's how the physics plays a very important role in the application of various natural things or the natural principles. So that's all for today's class. I hope you got a very good idea of electrical energy and how important it is for us to understand, to construct electrical circuits and electrical appliances in our day-to-day life. Have a good day, students. Bye bye.